Hello, my friends. In this video, we are going to use Maxwell equations to derive the speed of light. So the main title is to use Maxwell equation to see the light. Maxwell has four equations. The first Maxwell equation came from the Gauss law. Divergence of electric field is equals to charge density divided by epsilon. The second Maxwell equations came from Maxwell himself. The divergence of magnetic field is always zero. The third Maxwell equations came from Faraday's law. The curl of the electric field is equals to the negative of the time derivative of a magnetic field. The fourth Maxwell equations came from the Ampere's law. In this case, In this case, the curl of the magnetic field is equals to mu times a current. And this current is the sum of the displacement current and the conductive current. The conductive current is J. The displacement current here is epsilon times the time derivative of the electric field. So the first step is to apply the Maxwell equations to a dielectric medium. First, apply 1 to 4 to a dielectric medium. Dielectric medium is an insulating medium. It shouldn't contain any charge. So in this case, the charge density should be 0. And being an insulator, it should not carry any current. So the current density should be 0. The current density, the conductive current density J should be 0. If it is the case, it is fair to say that from equation 1, the rho here is 0, then the divergence of E, divergence of electric field should be 0. And in equation 4, the J terms on the right-hand side should be 0, because this is what we have assumed. Now the second step is to take the curl of equation 3. So second, take the curl of 3. Then the left-hand side of the equation 3 will be given by the curl of E. And the right-hand side is just the curl of the time derivative of the magnetic field. So let's label this equation as equation 5. Now to continue, we need to apply some vector identities. The curl of E can be written as minus Laplace and then E. And then plus the divergence and divergence of E. So divergence of E. So this is the this is the what we can get from the left side of equation 5. So let's write down here. The left side of equation 5 is the curl of E. But according to the vector identities, this can be written as a Laplacian of E. Do not forget the minus sign here. And then plus the divergence of E. But according to equation 1, the divergence of E is 0. So this term can go. Now we are going to take care of the right-hand side of equation 5. We have the curl, the curl of the time derivative of the magnetic field. And what we can do is to take the curl first and then differentiate the expression. So in this case, what we will end up with is the differentiation, the time derivative of the curl of B. But hang on a minute. The curl of B, according to equation 4, is given by mu and then times the time derivative of the electric field. So eventually, the expression can be further simplified into minus epsilon and then the second time derivative of the electric field. The left-hand side of equation 5 should be equal to the right-hand side of equation 5. So in this case, this expression here should be equal to this expression. So we have Laplacian of the electric field being equal to minus mu epsilon times the second derivative of the electric field. Second time derivative of the electric field, sorry. We have the minus sign in both sides of the equation. So we can just remove it. But hang on a minute. Laplacian of a electric field is equal to mu epsilon times the second time derivative of the electric field. Shouldn't this be a wave equation? A wave equation with the time with the propagation velocity given by 1 over square root of mu epsilon. And in free space, the this propagation velocity Vp is going to be 1 over mu naught, square root of mu naught and epsilon naught. And fortunately, this expression will end up with 2.9 times 10 to the power 8. And this is exactly the speed of light. And the unit of this Vp, the propagation velocity, is meter per second.